Math 1314, Tyler Junior College, 6.5 Cramer's Rule, Video 2, 2x2 Determinants. In the previous video, we talked about coming up with a gimmick for saying, I want to do this to these four numbers arranged in a square. Multiply one way, multiply the other, and subtract. Well, that's called a determinant, but before I can define a determinant, I need to define a few other things, starting with a matrix. Now, when most people hear the word matrix, they think of the trilogy with Keanu Reeves, and that's cute and all, but from a mathematical perspective, that's not what a matrix is. All a matrix is a rectangular array of numbers, and more specifically, an m by n matrix. Looks like a multiplication problem. An m by n matrix is a rectangular array of numbers with m rows and n columns. In other words, the very first number when you're describing the size of a matrix represents the rows. And the second number when you're describing a matrix represents the number of columns. So for example, here's, and a matrix is enclosed in brackets, the square looking parentheses. So for example, this is a 3x4 matrix. We're going to open up a matrix with some brackets, an open bracket, and we're going to put 3 rows and 4 columns. So if we're going to have 4 columns, let's start with the first column, and these numbers aren't picked for any particular reason. I'm just picking numbers at random. 1, 13, 71. So there's the first column, and notice that I've already established 3 rows. Maybe something like 1, 17, 2, or something like 11, 16, 72. And they could be negative, or they could be anything really, but I'm just choosing positive integers for the sake of simplicity. Or they could be negative. It could be something like 9, negative 28, and negative 45. And then we'll close it off because that's the end of the matrix. There is no limit to how large a matrix can be, but it does have to have at least 1 row and at least 1 column. So that's all a matrix is, a rectangular array of numbers. Now, a square matrix is a matrix with the same number of rows and columns. So for example, you could set up a 3x3 matrix by saying something like 1, 2, 7, negative 1, 8, 3, 4, 17, and pi. Pi is a perfectly good number. That's an example of a 3x3 matrix. It's a square matrix. Now, every square matrix has what's called a main diagonal. The main diagonal is the diagonal from the upper left corner to the lower right corner. Excuse me, that was not supposed to be a box. That was supposed to be, no, not a circle either. I know what I'm trying to do. There we go. That's what's called the main diagonal. There are some different phrases for the other diagonal being the one that would go this direction. I did not mean to make that pink. I meant to make this pink. Hold on. Some people call that the minor diagonal or the off diagonal or whatever. Well, but the one going from the upper left to the bottom right is called the main diagonal. Now I'm going to be using that in a little bit. Now, if you have a square matrix, there's a function that you can apply to it called a determinant. For any square matrix, we can define a function called the determinant, denoted as absolute value bars. When finding the determinant of a 2x2 matrix, we do not write the brackets, only the absolute value bars. Specifically, for a 2x2 matrix, the determinant is defined as follows. So we're going to set up a matrix, but inside of braces, meaning that we're going to, bracket, inside of vertical lines instead of brackets, meaning that we're going to find its determinant. And to generically represent a 2x2 matrix, we just need 4 generic numbers, aka 4 letters. We'll just call it A, B, C, D, lowercase. And remember in the previous video when we said we wanted to define something that says, do this product, and subtract? This is what the 2x2 matrix, the determinant of a 2x2 matrix is going to do. It's going to say, all right, I want you to find this product, so A times B, A times D, and I want you to find this product, B times C, and I want you to subtract them. And that's going to be the definition of this. Now, there are some people who are deeper into linear algebra who might argue whether or not that's actually the definition. The definition of a determinant is something else, and this is just the formula for it. But for our purposes, this is going to be the definition of the determinant of a 2x2 matrix, a 2x2 array of numbers. We multiply the main diagonal, so A times D. We multiply the other diagonal, in this case, B times C, and we subtract the two. Now, unfortunately, for larger matrices, such as 3x3 and 4x4, the determinant is defined differently. It's kind of defined recursively, meaning the way you find a 3x3 determinant is you do several 2x2 determinants, and the way you find a 4x4 determinant is you do several 3x3 determinants, which means you do a bunch of 2x2 determinants. But it's a little bit beyond the scope of this video. We're only going to be dealing with 2x2 determinants. So let's take a look at a couple of examples real quick. These are really easy to do. They're really easy to get used to. If we take the first determinant, the 2x2 matrix whose first row is 3, 4, and whose second row is 5, 7, then all we have to do is multiply the main diagonal first, so 3 times 7, the other diagonal second, so 5 times 4, or 4 times 5, it's multiplication, so the order doesn't matter, and subtract the results. Well, PEMDAS comes into place, or BODMAS, if you live somewhere besides the United States, order of operations, and we do the multiplication first, so 3 times 7 is 21, and 5 times 4 is 20, and then we subtract the products, and so this determinant is equal to 1. Now, when you have negatives, just proceed with caution, but it's still the exact same flow. To find a 2x2 determinant, you start by multiplying the numbers on the main diagonal. So, and I'm going to use parentheses and adjacency to imply multiplication. So -4 times -4. And then you multiply the numbers on the other diagonal, which in this case is 8 times -2. And then you subtract the two products. Now be very careful when you have negatives involved because the definition already has a subtraction in there. If we find the product of the first two, we'll get 16 minus, and if we find the product of the second two, we'll put these in this color blue. If we find the product of these second two, that's -16. Okay, I meant for this to equal 0, but it's not going to. That's okay. And then 16 minus 16, 16 minus -16 is positive 32. So calculating the value of a 2x2 determinant is really just a matter of finding the answer to two multiplication problems and subtracting the results. The main diagonal product minus the other diagonal product is the definition of evaluating the determinant of a 2x2 matrix. We're going to use that to solve a generic system of 2x2 system of equations.